In this lecture video, we look at inference procedures for two population proportions based on large samples. In particular, we're going to be developing procedures to test hypotheses about two population proportions. We'll also develop procedures for constructing confidence interval estimates of a difference between population proportions. So here's the sampling framework. Suppose we have independent random samples from two populations where we've sampled in such a way that each sample can be considered to be the result of a binomial experiment. Specifically, let P1 hat be the proportion of successes in sample 1, a sample of size n1 from population 1, in which the true population proportion is P1. Similarly, let P2 hat be the proportion of successes in sample 2, a sample of size n2 from population 2, in which the true population proportion is P2. We want to make inferences about P1 and P2. In particular, we want to compare them. Are they the same or are they different? If they are different, which is bigger, and what is the magnitude of the difference? We will use the sample proportions, P1 hat and P2 hat, to make inferences about the population proportions P1 and P2. Now, to do this, we'll need to understand the sampling distribution of the difference between the sample proportions P1 hat minus P2 hat. Now, recall that by the central limit theorem, for sufficiently large sample sizes N1 and N2, the random variable P1 hat minus P2 hat is approximately normally distributed with mean P1 minus P2 and standard deviation, which we'll denote this way, cap S with P1 hat minus P2 hat in the subscript. So this is we would read this as the standard deviation of P1 hat minus P2 hat, and that is equal to the square root of P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat over N2. Now, it follows then that the standardized quantity has an approximately standard normal distribution. So if we standardize the difference between the sample proportions, so P1 hat minus P2 hat minus the mean of its sampling distribution, which is P1 minus P2, divided by its standard error, or its estimated standard error, which again is this quantity here, the square root of P1 hat times 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat over N2. So I'm just using this more concise notation in the denominator here. Otherwise, it would take up too much space in that denominator. But anyway, so this standardized quantity, the standardized version of the difference in sample proportions for sufficiently large samples will be approximately standard normal. That is the basis then for developing procedures for testing hypotheses where we are comparing the two population proportions, and also for constructing procedures or developing procedures for constructing confidence interval estimates of the difference P1 minus P2. And so there are, again, three types of hypotheses that we can test, the same three types of hypotheses that we've been looking at for quite some time now. We have hypothesis A, which is a two-tailed test, hypothesis B, a left-tailed test, and hypothesis C, a right-tailed test. Now let's look at these in detail. So the two-tailed test, hypothesis A, has a null hypothesis that says that the difference between the population proportions is equal to some specified or hypothesized difference, which we're denoting by delta 0. The alternative hypothesis would be the opposite of that statement, and so therefore it would be that the difference between the population proportions is not equal to that hypothesized difference. For the left-tailed test, hypothesis B, the null hypothesis is that the difference in the population proportions is at least as large as delta 0, versus the alternative hypothesis, which says that the difference between the population proportions is less than delta zero. And then finally, the right-tailed test, in which the null hypothesis says that the difference in the population proportions, P1 minus P2, is less than or equal to delta zero, versus the alternative hypothesis, which says that P1 minus P2 is greater than delta zero. Now, in many applications, in many situations, the appropriate value to use for the hypothesized difference delta zero will be zero. But as we've said, in other situations, in the context, for example, in comparing population means and so forth, that in many situations, the appropriate value for the hypothesized difference will be something different than zero. And it really depends on the situation and the problem to be solved. So you really do need to be careful and think, and understand what is being asked in a particular problem or in a given situation to know what the appropriate value is for the hypothesized difference. Now, if the hypothesized difference delta zero is equal to zero in a given situation, then we can write the hypotheses as we've got here, substituting delta zero with zero. And so you can see that we can state the hypotheses either as a difference, which is the first bullet point under each of these hypothesis types, or via more directly as comparisons, as we've got in the second set of hypotheses, or the second bullet point under each type of hypothesis. Now, the test statistic depends on whether the hypothesized difference is zero or not. Now, if the hypothesized difference is not zero, then the formula for the test statistic is as follows. It's equal to P1 hat minus P2 hat minus whatever that hypothesized difference is, all over the square root of P1 hat times 1 minus P1 hat over N1, plus P2 hat times 1 minus P2 hat times N2. On the other hand, if the hypothesized difference is zero, then let's stop and think about this for a minute. If the hypothesized difference is zero, then under the null hypothesis, P1 and P2 are equal. And so we can drop the subscript. Let's let P represent the common value, the value of P1 and P2 under the conditions of the null hypothesis. And so in that case, what we would do is we would take the sample proportions and we would average them. We would pool them together to get an even better estimate of the presumed common population proportion. And so this is what we would have for the test statistic. It would be P1 hat minus P2 hat in the numerator, and we also have a minus zero here because that's zero is the hypothesized difference, but I'm not showing that there, right? We don't have to do anything with that. And then in the denominator we would have the estimated standard error of P1 hat minus P2 hat computed under the conditions or under the assumption that the null hypothesis is true. And that estimated standard error would be the square root of P hat times 1 minus P hat times the quantity 1 over N1 plus 1 over N2, where P hat is this pooled version of the sample proportion. Basically what we're doing here is we are combining the two samples and then calculating the proportion, the sample proportion for that combined sample. So you see the formulas here. Now, under the conditions of the null hypothesis, the sampling distribution of these test statistics is the standard normal distribution. As long as we have sufficiently large samples so that we can rely on the central limit theorem or appeal to the central limit theorem, and so that it would the normal distribution would provide an adequate approximation to the true sampling distribution of the test statistic. Okay, so then the rejection criteria. If we have a two-tailed test, we would reject the null hypothesis if the test statistic is either really small or really large. Specifically, if z-calc is less than negative z sub alpha over 2, or if z-calc is greater than positive z sub alpha over 2. For a left-tailed test, we would reject the null hypothesis if z-calc is less than negative z sub alpha. And if we have a right-tailed test, we would reject the hypothesis test, the null hypothesis, for large values of the test statistic z-calc. So specifically, if z-calc is greater than positive z sub alpha. The formulas for the p-value should look very familiar. They're the same formulas that we've had for other what we might call z-tests. Test where we go to the standard normal table to get the critical points. And so for the two-tailed test, the formula for the p-value is 2 times the probability that a standard normal random variable z is greater than or equal to the absolute value of the test statistic z-calc. So I see I have a typo here. I need to change these inequalities to non-strict inequalities. So let me do that. Okay, so there I've fixed that notation. So we see here then that the p-value for the two-tailed test is 2 times the probability that the standard normal random variable is greater than or equal to the absolute value of the test statistic. The p-value for the left-tailed test is equal to the probability that the standard normal random variable z is less than or equal to the observed value of the test statistic. And for the right-tailed test, the p-value is equal to the probability that the standard normal random variable is greater than or equal to the observed value of the test statistic. All right, so to develop confidence limits for P1 minus P2, we note again that for sufficiently large sample sizes, P1 hat minus P2 hat, and I need to fix that typo as well, but minus P1 minus P2 all over the standard error of P1 hat minus P2 hat is approximately standard normal. Okay there, so that's fixed. So this implies then that the probability that this standardized version of the difference between the sample proportions is less than or equal to z sub alpha is 1 minus alpha, or at least approximately equal to 1 minus alpha. We can rearrange stuff inside the parentheses there to get P1 minus P2 on one side of the inequality all by itself. And so this implies then that the probability that P1 hat minus P2 hat minus the z sub alpha times the estimated standard error of P1 hat minus P2 hat being less than or equal to P1 minus P2 is also approximately equal to 1 minus alpha. And so this implies that in repeated sampling, the random variable P1 hat minus P2 hat minus z sub alpha times the estimated standard error of P1 hat minus P2 hat will be less than or equal to the difference in the population proportions P1 minus P2 approximately 1 minus alpha times 100% of the time. Equivalently, the difference in population proportions P1 minus P2 will be greater than or equal to that same random variable approximately 1 minus alpha times 100% of the time. And so for that reason, the random variable that we're working with here, P1 hat minus P2 hat minus z sub alpha times the estimated standard error of P1 hat minus P2 hat, that quantity, that random variable, is a 1 minus alpha times 100% lower confidence limit for P1 minus P2. Now, once we have our sample and have computed that lower confidence limit, we say that we are 1 minus alpha times 100% confident that P1 minus P2 is greater than or equal to this lower confidence limit. Okay, similarly, the probability that this standardized version of P1 hat minus P2 hat is greater than or equal to negative z sub alpha is approximately equal to 1 minus alpha. We can rearrange the quantities inside the parentheses to get P1 minus P2 on one side of the inequality all by itself. And so this implies that the probability that this random variable here, P1 hat minus P2 hat, plus Z sub alpha times the estimated standard error P1 hat minus P2 hat, is greater than or equal to P1 minus P2. That probability is approximately 1 minus alpha. That implies that in repeated sampling, the random variable P1 hat minus P2 hat plus Z sub alpha times the estimated standard error of the difference in the sample proportions will be greater than or equal to the difference in population proportions P1 minus P2 approximately 1 minus alpha times 100% of the time. Equivalently, the difference in population proportions P1 minus P2 will be less than or equal to this random variable, approximately 1 minus alpha times 100% of the time. And so for this reason, the random variable P1 hat minus P2 hat plus Z sub alpha times the estimated standard error of P1 hat minus P2 hat, that random variable is a 1 minus alpha times 100% upper confidence limit for P1 minus P2. Now, once calculated, we say that we are 1 minus alpha times 100% confident that P1 minus P2 is less than or equal to this upper confidence limit. Now, if we compute both a 1 minus alpha over 2 times 100% lower confidence limit, given by this expression, and a 1 minus alpha over 2 times 100% upper confidence limit, given by this expression, and if we put those limits together, then what we have a 1 minus alpha times 100% two-sided confidence interval estimate of P1 minus P2. And that is also given right here. And so we say then at that point that we are 1 minus alpha times 100% confident that P1 minus P2 is somewhere in this interval. So that's how we construct a lower confidence limit, an upper confidence limit, as well as a two-sided confidence interval at a given level of confidence. We've seen this kind of development before. Let's take a look at some examples. And so this example is a comparison of male and female voters. So a candidate for political office wants to determine whether there is a difference in his popularity between men and women. To establish the existence of this difference, he conducts a sample survey of voters. The sample contains 250 men and 250 women, of which 42% of the men and 51% of the women favor his candidacy. Do these values indicate a difference in popularity? Test using a significance level of 5%, and in addition, construct a 95% confidence interval estimate, a two-sided confidence interval estimate for the difference in favor between men and women. And so let P1 denote the proportion of men voters who favor or who prefer the candidate, and P2 the proportion of women voters who prefer the candidate. The hypotheses to be tested are as follows. The null hypothesis is P1 minus P2 equal to 0. In other words, P1 equal to P2, versus the alternative hypothesis, which says that P1 minus P2 is not equal to 0. In other words, P1 not equal to P2. And we are to use a significance level of 5%, 0.05. Now, because the hypothesized difference is 0, in order to calculate the test statistic, we need to calculate a pooled estimate of the presumed common population proportion. And so we would first calculate P hat, which is going to be N1 times P1 hat, plus N2 times P2 hat all over the sum of the two sample sizes. And again, what we're doing here is effectively calculating the proportion of those who favor the candidate across the two samples. Once we had p hat, then we would plug that into the denominator here in the formula for the test statistic to get the estimated standard error of p1 hat minus p2 hat, which is in the numerator of that test statistic. The rejection criteria is to reject the null hypothesis if zcalc is either less than negative 1.96 or if it's greater than positive 1.96. All right, so now we can calculate the value of the test statistic. So note first that the pooled estimator of the presumed common population proportion is equal to 0.465. So 250 times 0.42 plus 250 times 0.51, all over the sum of the sample sizes, which would be 500. And then, so that's that's p hat. We plug that into the denominator of the test statistic to get the estimated standard error. We also have to calculate the point estimate of the difference in the population proportions, which is the numerator of this test statistic. And so zcalc, the test statistic, is equal to negative 2.017. Now, since negative 2.017 is less than negative 1.96, we reject the null hypothesis and conclude that P1 minus P2 is not equal to 0. In other words, we conclude that P1 is not equal to P2. And so there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists in the proportions of men and women voters who favor this particular candidate. Next, we construct a 95% confidence interval estimate for the difference P1 minus P2. The estimated standard error of P1 hat minus P2 hat is given by this calculation, and it's equal to 0.04443. The 95% confidence interval then is equal to P1 hat minus P2 hat minus plus z sub 0.025, the interval coefficient, which is obtained from the standard normal table, times the estimated standard error of P1 hat minus P2 hat, which again was 0.04443. And we plug these values in, and we get the interval that ranges from negative 0.1771 up to negative 0.0029. Now notice that 0 is not in this interval. And because of that, we know then, even if we had not done that hypothesis test, if we were to perform that hypothesis test at a 5% significance level, we know that we would reject the null hypothesis, again, because 0 is not in this interval. And again, see, that is the conclusion that we came up with, isn't it? And so to interpret the interval, we would say that we are 95% confident that the difference in the population proportions, P1 minus P2, is somewhere between negative 0.1771 and negative 0.0029. We could also add P2 to each of these pieces throughout this chain of inequalities. And so then we would conclude that at 95% confidence, that P1 is anywhere from, or is between P2 minus 0.1771 up to P2 minus 0.0029. So that is how we develop procedures for comparing the proportions of two populations using large samples that are large enough for us to appeal to the central limit theorem and for the normal distribution to provide an adequate approximation to the true sampling distribution of P1 hat minus P2 hat.